Okay, so this is the yo-yo that we were studying the other day, the last week probably. Have you ever played with the yo-yo? Okay, so most of you already know. So if you haven't before, you can just play it during the break. And also your quiz 5 is over here. You can pick up your last quiz. Now, before we start, any questions? Sure. This one. Okay, this one.
I cannot understand that what it does imply.
Okay, so one thing is to check that this indeed satisfies this equation. So you can just put this over here and this is what you would get. Now what are these terms? So this term is basically the underdriven oscillator. So it says that the oscillator there will be a component of the motion, a part of the motion which it will be as if there is no force acting on it. Plus there is this part which is created by the force. You see, this can be, the external force can have a different frequency than the frequency of the oscillator itself. So if you leave the oscillator to itself, it will have this motion. It will oscillate with frequency omega 0. But since you are pushing it with frequency omega, it can also move with if this is 0, it can move with the frequency omega. This is the part that is caused by the external force.
So position.
This is the position of the object. The whole thing is the position. Of course, given the initial position and the initial velocity, you can determine what A and phi 0 should be. But once you determine that, the whole thing determines the position of the object as a function of time. So it's as if the object is doing two different oscillations at the same time. One is at its natural frequency, the other one at the frequency of the external force.
It's also an oscillation position.
Yes, but this need not be periodic, by the way. Although this term is periodic, meaning that each one of these terms, they repeat themselves after a given time. These two periods might be different, so that the whole motion, the sum, need not be periodic. It doesn't repeat itself at all.
There is a force and we divide it something. The second.
Now, we are not really dividing it into anything. This is the equation we have. This is the force, we take it as a whole. But the motion can be, in a sense, divided into two parts. One part with the frequency omega 0 and another part with the frequency omega. But it's not just two different oscillators. It's the same oscillator moving with this function. It has both of these motions at the same time. Just imagine it like this. You are swinging back left and right. Okay, just as if there is a music playing, you are swinging left and right, and at the same time you are rotating your finger. Okay? So this is the motion of your finger. There is this oscillation, there is also this oscillation. So the motion of your fingertip needs both of these terms. Or if you have looked at in your homework, in the question in one of the questions you are required to study the motion of a point on a rolling disc. Now that point is both rotating around the center of mass, plus the center of mass is moving with constant velocity. So to find the exact trajectory of that object, you have to add these two motions together. So that would give you the motion of that point. It's just like this over here. There is one term, this is the natural oscillation of the object. On top of it, the external force creates another oscillation. And the exact description of the motion or the position of the object as a function of time needs to have both of these terms superposed. This is kind of another superposition principle.
these forces arbitrarily defining F equals omega t?
No. I mean,
How do we know?
well, up to now you have always identified what the forces are. Okay, there was the friction force, there was the gravitational force, there was some kind of a friction, some kind of a force acting on the system. Now, in this case is a bit different in the sense that the force depends on time. Okay, there is a time-dependent force. What can it be? Well, the example that we had used was your swinging motion. If you are on a swing, you want to accelerate, what you do is you just swing back and forth. In that case, your motion is creating this force. Now, another thing that you will learn probably next year. Well, we had already talked about the Taylor expansion. Now, Taylor expansion tells us that any function, if it is sufficiently well behaved, can be written as a polynomial, infinite, or a polynomial of infinite order. So you can just write it as if you have any function, it will be just f of x will be just a0 plus a1x plus a2x squared plus etc. Any function. Now there is another theorem called the Fourier expansion, which tells me that if you have any function, any periodic function, whatever the period is, any periodic function can be written as a0 plus sines and cosines. It's just like, in a sense, it's like the Taylor expansion, but instead of the polynomials, you are using so-called harmonic functions. So this is just a typical term in that expansion. So this one over here is just a typical term in that expansion. If you are just summing all of them, you see in this solution also, you see that there is one term, this is the zero force term, plus one force term. If you have two different forces, then you just add the corresponding solutions to each other. So if you have just the sum of sines and cosines, each one we know how to solve it, then the exact solution will be just the sum of all of them. Anyway, this thing you will learn next year. But this is just a typical example. All the periodic forces, you can write in terms of terms like this.
There is a mass hanging on speed.
Okay.
We pull it sample is.
Okay.
Then it's began to do periodic motion. But there's also drag force.
Black holes.
Drag force.
Drag force. Okay.
Because of the drag force, it's doing underground.
True.
But in the underground motion, ideally, it will never stop.
True.
But in this example, we know that it will stop.
Well, at least its motion goes below our measurement, the sensitivity of our measurements. That is what we know. You see, our experimental device, measurement device, have a certain sensitivity. It cannot measure displacements smaller than a threshold value.
Actually, it will not stop.
Well, ideally, no. But in real life, of course, if the motion gets smaller and smaller, there will be other effects, and it will, of course, stop. Well, stopping is also another, in itself, a problematic issue, because if you have any extended object, well, the atoms are always moving. So how do you say that whether it's moving or not? What do you mean by stopped? How do you measure it? Even in this case, it eventually goes, the displacement goes, even in the idealistic case, the displacement, the amplitude goes below the experimental sensitivity. So that's what we most of the time mean by stopped. Okay, let me go to Kepler. Do you know when was his birthday? Well, today is the best choice you have, best guess you have. But no. Unfortunately, we didn't have a lecture on his birthday. Now, the next best choice, best guess. What? Well, that is the next best guess today or plus minus 1 day. Even that is not correct. The next best guess. 2 days ago. Yes, it was 2 days ago. Now, okay, I'm kind of switching the order of the material covered in the book on purpose because, you see, when I was a student, I also studied Kepler's law in my general physics course, and it was, of course, taught after the Newton's law of gravity. And once you study Newton's law of gravity, it's just the Kepler's 3 laws, well, not the first one. The second and the third laws are just trivial consequences of Newton's first law. So I was like, okay, who cares about the Kepler's law? So what's so special about the first one? So it's just trivial. But when you put things in context, in the historical context, things become more interesting. You see, Kepler was born before Newton. I mean, he died before Newton was born. So Kepler didn't know the calculus. Kepler didn't know about the Newton's law of dynamics. There was no theory of dynamics. And people were looking at the universe, at the so-called heavens at that time, and they were trying to understand what causes and what kind of motion do they have and what causes that motion. And what Kepler knew, for example, this is one of the trajectories of one of the planets. This is Mars. And this is, I mean, people could measure the distances of the planets. They could measure at which orientation they are. So they could determine the trajectories of planets. And at that time, also thinking about the philosophical context and the religious context of that period, of course, human beings were the center of the universe, the main purpose of the universe. So they had to be at the center. This is the Earth. So Earth has to be at the center of the universe. And, well, this was the trajectory of Mars. And if you follow the trajectory, I mean, you see, for example, let's assume that it's rotating in the counterclockwise sense. Okay, it has an angular momentum towards you, but here now, at this point, it has an angular momentum into the screen. I mean, even the angular velocity changes. So if you just follow the trajectory of Mars, it goes like this, and then for some reason, it stops here, goes back, and then forward, and then back, forward, etc. So this was what people believed was the trajectory of the motion. Now then comes the first law. I mean, some of you were asking, so what's the point in the first law? Well, I would say it's probably the most important revolution in scientific history. It did 2 things. First of all, from this picture, we went to this picture, sorry. Here is the sun. And from that all complicated, okay, so this was the assumed trajectory of Mars. And from this one, we went to this one. Now, how does one see such an ellipse from such a trajectory? I have absolutely no clue. I mean, you have all these kind of randomly looking motion, randomly looking numbers, and you just somehow see that if you go to another coordinate system, if you just shift your origin, not from Earth to the Sun, everything becomes simple. You just obtain a simpler description of the motion of the objects. Now, there were other people before Kepler who were trying to claim that Earth might not be at the center of the universe, and they were killed because of such claims. So nowadays we just take it for granted that, I mean, the sun is at the center of the solar system, etc. But at those times people would be killed because of claiming such things. And Kepler, I think, is the first one who survived after such a claim. So this is the first, let's say, it's not just about our understanding of the nature, but it's just the revolution in the human understanding of how to do science. Now, just to give you an idea, one of the most difficulties you're having this year is that you have to do such a revolution within 1 year. So on one hand, you have all your high school training on how to look at nature. On the other hand, now you are supposed to look at nature as a scientist. I mean, before and still you are, it seems that most of your concerns is concentrated on what will be asked in the exam. Or will you be able to solve the questions in the exam? So that is, I would say, the least important. Now, of course, Kepler didn't have this great pressure which you have, unfortunately, but you should also realize what this great pressure is doing to you. Now, this is the first law. Now, the second law, again, he just has the numbers. He doesn't have any theories. The first thing he did was just move the center of the trajectory to the sun. Well, he says that it's an ellipse with the sun at one of the focal points. Now, what's an ellipse? Okay, it just looks like this, but what's the definition of an ellipse?
Maybe not. We have 2 points, we call them focus points, and a point always length of sum of the length to 2 points is equal.
True. I mean, basically, if you want to draw an ellipse, just take a string of some length, fix the 2 points, leave it a bit relaxed. I want one going here. Keep these points, both of them, fixed. And take your finger. No, you keep that fixed. And just move your finger around. So you see, the distance of my finger from these 2 focal points is just the sum of this length plus this length, which is the total length of the string, which is fixed. So this will draw an ellipse. Oops. Thank you. Now, one thing is we will eventually discuss the Kepler's second and third law using Newton's dynamics. We will not be discussing the first law. I mean, because it takes around one hour to show that starting from Newton's laws, we can actually prove that the orbits have to be ellipses. So if you are interested, I would advise you to look at Feynman's lost lecture. This is a book. I mean, you can also find it in Turkish. It has been translated by TÜBİTAK. So it's like 50 pages. It's not that long, but more than half of this book is devoted to the discussion of the ellipse. Because without really understanding what an ellipse is, you cannot really prove that the trajectory is an ellipse. Now, the second law just says that, so this is the trajectory of a planet, and you just follow this planet. So let's say this is at some point, at some time it's at this point, at the next time it will be at this point, so after delta t, and you just look at the position of that planet at a different time. You see that it is at some point at this time, and you wait the same amount of time, delta t, it will be over here. Well, you have these 2 areas, let's call them A1 and A2. So A1 is equal to A2. Now again, I mean, remember Kepler just had this bunch of numbers and nothing else. He didn't even have a calculator. So from those numbers, how can one think of looking at these areas and see that they are actually equal for whatever delta t you take and whatever time you take? I mean, this slice over here can be somewhere over here, and at whatever point you look at it, the rate of sweeping of area, this is what's called at a given time, the area swept by this radius vector is always the same. This is Kepler's second law. And now let's come to the third law. Let's say you have two different planets. This is the sun, this might be one planet. This will be the other planet. Planet 1, planet 2. And let's just assume that, okay, this is, let's call this distance 2r1, and this distance 2r2. This is what's called the major axis. So you see, if you have this ellipse shape, this is the longest line in the ellipse. This is called the major axis, and this is the shortest line that you can draw between, well, not the shortest one, but let's say it goes through the center. The shortest line that goes through the center is what's called the minor axis. And half of this major axis is what's called the semi-major axis. Now, the semi-major axis of this orbit is R1, and the semi-major axis of this orbit is R2. And if you just say that this planet completes one full rotation around the sun in T1, say, and the duration of one full rotation of the other planet, let's call it T2, and what Kepler observed was T1 squared over R1 cubed. This is equal to T2 squared over R2 cubed. This is Kepler's third law. Of course, these are just the statements of Kepler's third laws. Now we will try to understand these Kepler's third law. We already know Newton's dynamics in terms of the concepts that we have developed using Newton's dynamics. So what does these laws mean? Now let's start with the second law. If you remember what Kepler's second law was, okay, A1 is equal to A2, or you can also say that A1 over delta T is equal to A2 over delta T. Now, the advantage of writing it in this form is that you see A1 is the area swept in a time delta T. So A1 over delta T is nothing but the rate of sweeping of the area. So this area over delta T is the rate of sweeping of area. So Kepler's second law basically states that this rate is conserved. It doesn't change during the motion of the planet. So let's try to write this rate of sweeping of area in terms of the radial distance, in terms of the velocity or the speeds and the angles and all the kinematical variables we have. Now let's just imagine that this is the sun. This is just a segment of the trajectory of my object. So this is the initial radius vector, and then this radial vector, it just sweeps after some time delta t, it becomes like this. It changes its position, and it sweeps an area delta A in a time delta t. Now, what we would like to calculate is delta A over delta t. and assuming that eventually we will take the limit that delta t goes to 0. Now at this instant, it also has a velocity, let's say v. So here we have our planet at our initial time. It is moving with a velocity v such that after a time delta t, its position becomes r2. Now this length over here, which is more or less this length over here, because remember we are taking delta t very small. In a very small amount of time, the velocity doesn't change much even if it's accelerating. If the velocity doesn't change much, if it is almost constant, it just means it's going over almost a straight line. So this distance over here is just v times delta t, the speed times the time interval we are looking at. Now here we have a triangle. Let's say this angle over here is theta. This angle. This is the height of the triangle. Now the height of this triangle is nothing but v delta t. No, sorry, the graph over there is somewhat incorrect. This is v delta t, the length of that straight line. Now this height is nothing but v delta t times sine of theta. This is the height of the triangle. What is the area of that triangle? The area of a triangle, height times the base, half of that, 1 over 2 v delta t sine theta. The base has length r1. This is delta A, and we are dividing by delta t. This is equal to 1 over 2 v sine theta r1. And Kepler's second law basically states that this is constant. Well, 1 over 2 is also a constant, so v times sine theta times r is constant. Now I'm just dropping this r1 because v is the velocity at this time, r is the distance from the planet at this time, and theta is this angle over here that the radius vector and the velocity vector makes with each other. Of course, as the planet is moving around, r will be changing, v will be changing, theta will be changing, but this combination is just constant. What is this combination? It's almost a vector product. Well, there is just a slight catch. You see, this angle over here between r1, r and v is pi minus theta. But sine theta is sine of pi minus theta. So v r sine theta is equal to v r sine pi minus theta. Well, as your friend pointed out, this is nothing but the magnitude of a cross product, because we have the radius vector, we have the velocity vector, we have the radius vector, the velocity vector. The angle between these two vectors is pi minus theta. So this is equal to the magnitude of r cross v. Well, let me just multiply by the mass of the planet and divide by the mass of the planet, 1 over m r cross p. Now, does this remind you of anything? R cross P? It's the angular momentum. So this basically states that Kepler's second law is nothing but the conservation of angular momentum. Well, it's not exactly, but if you add, because you say the conservation of angular momentum tells us that the vector is conserved. Here, the Kepler's second law just tells us that the angular momentum, the magnitude of the angular momentum is conserved. But now let's add the first law, because first law tells us that the trajectories of the planets they just lie on a plane. The radius vector and the momentum plane, they always lie in the same plane. Ellipse is just a shape that lies on a plane. So first law tells us that the r cross p, the direction of this r cross p is perpendicular to this plane, and first law states that this line perpendicular to the plane is also constant. It doesn't change. So essentially, first plus the second law tells us that the angular momentum of the planet is conserved. So what are the conditions for the conservation of angular momentum? No external torque, well, one thing is there is external force. You see, this is the trajectory of the planet, this is the sun, and this is the trajectory of the planet. So if the planet is definitely accelerating, so there is an external force acting on the planet. And, well, just one more thing to note. This is the angular momentum relative to the sun. So we take the sun as our reference point and calculate the angular momentum of the planet relative to the sun. So there is an external force, but if angular momentum is conserved, there shouldn't be that external force shouldn't be creating an external torque. So what can you conclude from these two? What should be you should be able to tell me one property of this force.
This force passing through the sun.
It should pass through the center. Otherwise, it will create a torque. So there is a force that doesn't create a torque. It just means that that force, the direction of that torque should be parallel or anti-parallel to the radius vector. So again, Kepler's second law tells us that the force acting on this planet, it can be some function of the position, we don't know, but it definitely has to be in the radial direction. So already from Kepler's second law, Newton could conclude that whatever this force is that causes the planets to orbit the sun, it has to be in the radial direction. It might be pointing outward, well, it's kind of accelerating towards the sun, so it has to be radially inward. But it cannot be pointing out in any other direction. So that is one conclusion that Newton could drive because of the work of Kepler. Now, any questions on this? Why planets move to start with? Well, up to this point, I will just tell you that it's an observation made by Kepler. Kepler just followed the trajectories of the planets, and that is what he observed. That is what he saw. He didn't have an explanation for that. He didn't know why. But that was what he observed. Later on, Newton could tell why. Now again, starting from the force, and we will be first trying to drive what is the force acting on these planets. Then the next question we can ask to prove the Kepler's first law would be, under this force, what will be the trajectory of the planet? But that will be the last one. Other questions? Now let us look at Kepler's third law also before we give a break. Now, one of the special kinds of ellipses is what we call the circle. If these two focal points, you see the ellipse we defined as we fix 2 points and we just move the finger around, stretching this string. Now, these 2 points that are fixed are what we call the focus of the ellipse. If we just take these 2 focal points to be the same, then what we obtain is nothing but a circle. So whatever Kepler's laws are, they will also hold for they should also hold for circular orbits. Now, also, although Kepler knew that the orbits of planets were ellipses, they are almost circular. The major planets, they all have almost circular trajectories. Only the comets, they don't have a circular orbit. Okay. Let's look at the circular orbit and try to calculate what the force is. Now we know that the period squared over the r cubed, this is just constant. This is what Kepler told us. Now an object, let's say this is the sun, it is going around the circular orbit. It has a speed v. Now if it's going around the circular orbit, and also remember r times v times sine theta. This we know that this is constant. Now for a circular orbit, theta is pi over 2. R is just constant. Theta is constant. So this Kepler's second law tells me that v should also be constant. So if the planet is moving around the circular orbit, in that case, the speed of the planet should be constant. We don't yet know energy conservation. We are not using energy conservation because Kepler didn't know about it. But nevertheless, Kepler's second law just implies that the speed of the planet, if it's moving over a circular orbit, should be constant. Now, the period of the motion would be, well, the planet covers a distance 2 pi r with a speed v, so this is the period. Or we can say that v is equal to 2 pi r over t. Now, if it's going around the circular orbit, we know its acceleration. Acceleration is v squared over r. So this tells me that 2 pi squared r over t squared. This is the acceleration. Well, we have r squared. Here we also have another r, so we just cancel. So the force acting on this planet is just mass times the acceleration. A is 2 pi squared r over t squared. The force, the magnitude is the mass of the planet times the acceleration. So this is 2 pi squared m r over t squared. Now let's just multiply it with r cubed and divide by m. This is 2 pi squared r cubed over t squared, no, r squared. But Kepler tells us, Kepler's third law tells us that this r cubed over t squared is just a constant. It's the same for all the planets in the solar system. 2 pi squared is also just a constant. It's the same for all the planets. So this from Kepler's third law, we can just conclude that this is just a constant for all planets in the solar system. We already had determined the direction from Kepler's second law. We know that the force is a radial force. It's pointing towards the sun. Now this law, the third law, tells us what the magnitude of this force has to be. If this force acting on each planet should be proportional to the mass of the planet and inversely proportional to the radius squared from the distance from the planet. So Newton just didn't come up with this 1 over r squared law. I mean, he didn't even measure it. It was Kepler, and from Kepler's third law, he could conclude that the force acting on planets had to be inversely proportional to the radius squared. And it has to be proportional to the mass of the planet itself. Now, any questions? We will see that they will be different. I mean, this constant, we will see that it depends on the mass of the sun also. So if you go to another system, then of course this constant will depend on the mass of the corresponding planet. Corresponding stars. But we will see that. That will be our next step. So we now know the proportionality it will be in fact Newton's third law, which tells us that this force should also be proportional to the mass of the star, not only the mass of the planet. And we will call the proportionality constant this Newton's constant. Any other questions? Okay, so I'll see you after the break.
For this question.
Yes.